Swayam Prabha. Digital India. Educated India.
Welcome. In the last couple of lectures, we have discussed about the mixing and phase separation behavior of liquid solutions. We started talking about the Gibbs energy to begin with, but then we said we can write the Gibbs energy in terms of Helmholtz free energy density, F of Vt, and then later on we said that how that single function basically characterizes first the mixing and phase separation behavior. Then we can also write the osmotic pressure and the chemical potential in terms of that function F of Vt. So although we have not really said how we will get that particular function, we already know what that function form should be for having a mixing behavior or a phase separation behavior. Okay. So I want to take it further and talk about the phase equilibrium, where you must have done this in mass transfer course and other courses, that we talk about phase equilibrium in terms of equality of chemical potentials of components. So how does our description in terms of F of Vt for liquid solutions will adapt for the case of the phase equilibrium? And I want to show that again that single function is all that you need, and it is a very convenient way to look also also for the phase equilibrium. Okay. So just to briefly recall what do we mean by a phase separation. So we can start with a certain volume fraction phi and a volume V in a beaker, and this thing will phase separate into two layers, phi A, Va, phi B, Vb, provided that the final free energy ends up becoming lower than the initial free energy before phase separation. Okay. But now once it is phase separated, then in that case if I want to know the volume fractions phi A and phi B, we can use the idea that for any component the chemical potential in the two phases must be equal, that is given again by thermodynamics, but at equilibrium. So at thermodynamic equilibrium, we know that the chemical potential, the other way to think about it is, let us say the chemical potentials are not equal in the two phases. So if they are not equal, then the solute molecules will go from higher chemical potential to a lower chemical potential, whatever that direction is, and this will continue to happen until the chemical potential becomes equal. Okay. So only when the gradient of chemical potential ceases that we get the equilibrium conditions. The same thing I can do for the solute. And now since we said that the osmotic pressure also characterizes the mixing behavior, the same thing must apply for osmotic pressure as well. So if say one layer or one phase is at a higher osmotic pressure, then solute particles will move from there to solute or solvent particles will move from that layer to a different layer, and so this will continue until equilibrium, where the osmotic pressure also becomes equal. Okay. In fact, we can think of both the chemical potential and osmotic pressure as some kind of a driving force for diffusion. So, mu s, mu p and phi are all driving forces for diffusion, and in fact all can be written in terms of f of Vt. Okay. So, we will do this derivation now and try to see like how does these expressions become in terms of the f of phi that we have discussed. Okay. So, let us first look at the solute chemical potential that we said is well, again just for convenience sake I will write the expression in terms of f of phi. I will not put a temperature there, but keep in mind that the f is also a function of temperature, because nowhere in the derivation we are going to make any assumption regarding the temperature. We do not assume it is uniform or anything. So, then if I do mu p phi a is equal to mu p phi b, that gives me this, and we have certain cancellations, and what do we get is f of phi a minus f of phi b is equal to 1 minus phi b f prime of phi b minus 1 minus phi a f prime of phi a. Now, we can also write the same thing for equality of solvent chemical potential, but let us first write for the osmotic pressures. So, we know the osmotic pressure is the following. So, we have again we have certain cancellations. So, we have derived two relations, both of which have the same left hand side. So, we can compare the right hand side in 1 and 2. and what we do get is I am sorry, please note here that there is a small error here. So, we have phi A, F phi A, phi B, F prime phi B. So, now we have phi A, F prime phi A minus phi B, F prime phi B, and then this thing is equal to, so this will move on that side and we have cancellation of phi B here. Similarly, this will move on that side and we have cancellation of phi A here, and what do we get is simply F prime phi A is equal to F prime phi B. So, now what we get is that to attain the phase equilibrium, the derivative of the Helmholtz free energy densities at the 2 point must be equal. That is one thing. Now, we can put 3 into say 1, the expression we have written earlier, and what we do get is f of phi A minus f of phi B is now equal to, so f prime is anyway same for both, and it is 1 minus phi B minus 1 minus phi A. Using that, what we get is f prime phi A, which is equal to f prime phi B that we have got from 3, is equal to f of phi A minus f of phi B divided by phi A minus phi B. So, this tells me the concentrations that will occur at phase equilibrium in the two phases. Okay. And now, let us see how exactly we can also interpret in a graphical way. It is called a common tangent construction that can really help us talk about phase equilibrium in a way that we can intuitively feel from a graph. So, let us say that the function has certain form like this. There is a particular reason why we have drawn in this way that will be clear to you in a moment, and we want to know that what should be the concentration of the two phases in the case of phase separation. So, the first thing is that whether we will have a phase separation here or not. We of course have, because there is clearly a convex part here for which f double prime is lower than 0. We do not know for the entire plot. For the entire plot, of course, it has both concave regions and convex regions. So, it is very difficult to say from the graph, but of course, since it has a negative f double prime somewhere in the graph, the system should phase separate, okay, depending on what is the concentration I begin with. So, if it does phase separate, then in that case we have derived So, now you can see that f prime here characterizes the tangent to the graph, and the tangent should be equal at 2 points. Okay. The tangent should be equal at 2 points, that is one condition, and the second condition is that the tangent value should be equal to, the slope of the tangent should be equal to this particular thing. It turns out it is only true if I draw a tangent that is common between the 2 points in this particular way, and this is called a common tangent. So, let us say if I start with some phi here, the only condition here is for that value of phi, f double prime must be less than 0. So, for if that phi f double prime is less than 0, the system will phase separate into phi A and phi B, or the other way around. And we can say like how we recover this particular relation, because we can do a construction here. So, for this particular triangle, the slope is equal to this divided by that. This is of course f prime, f of phi B minus f of phi A, and this distance along the x direction is equal to phi B minus phi A. So, if I calculate the slope of the tangent, that is slope which is what essentially what we have here. Simply if I just take a minus sign on both top numerator and denominator, we do recover the relation we have. Of course, we can interchange phi A and phi B, it makes no difference in the whole scheme of things. Okay. So, there are two things to get from here. The first thing is we can write the phase equilibrium in terms of a function f that we have discussed earlier, and the second thing is that the equilibrium compositions will of the two phases will correspond to the common tangent, and of course, the system will phase separate only when, if I start with a value of phi, the second derivative of f must be less than 0, that is the condition for the phase separation. So, now let us look at in more detail that why we have drawn this particular graph as opposed to a completely convex graph. So, what will happen in the case when the graph is fully convex, and then we will discuss in more detail that what happens in other portions of this graph. So, let us say if the graph was unlike what we had earlier, and let us say the graph was like this. Okay. So, one thing you can clearly see from here, that if the graph was like this, we can no longer draw a common tangent that passes through 2 points on the graph. So, let us say if I draw a common tangent here, if I draw a tangent, I cannot draw a tangent that passes through 2 points. So, I can draw tangents at different points, but they do not really touch any other point on the graph. What essentially it means that in this particular case, we do not really have a circumstance when we will have two concentrations which are different and they are in equilibrium. in this case the system will have a tendency to phase separate completely. There will be like a complete demixing. One of them will have a volume fraction of 0, the other one will have a volume fraction of 1. And we will not really have any kind of a coexistence of two different compositions. Only when we have a function graph like this, we can do like a common tangent, and we can have a circumstance where there are two different volume fractions in the two phases, and we do not have a complete demixing. So, in this case we will have a complete demixing, that is phi A is equal to 0 and phi B is equal to 1, and in this case we can have phi A, phi B both higher than 0. Okay. So, now let us see like what happens on the other part of the graph. Let me again draw a common tangent in this case. So, if I look at the middle arm, it goes from a convex shape to a concave shape. So, right here f double prime is higher than 0, right here f double prime is less than 0. So, there must be a point in between that should be like an inflection point at which f double prime will be is equal to 0. Similarly, we may have an inflection point here f double prime equal to 0, because again f double prime is becoming higher than 1. So, if I look at these two particular points, and let me call that something like phi A star and phi B star, then if I am in between the phi A star and the phi A star and phi B star, then in that case f double prime is higher than 0, f double prime is less than 0, and then we always have a phase separation. But what happens when we are in the other two regimes, that is, let me highlight here. This is a middle regime, that is when we have f double prime is higher than 0, but you also have two other regions, one here and one there, that for which f double prime is actually higher than 0, right. So, this part in the middle is known as a unstable region, and these two parts are known as metastable regions. So, the system is unstable when phi is higher than phi A star and less than phi B star, and metastable when phi is higher than phi A, less than phi A star and higher than phi B star and less than phi B. And what really happens in these two regions is, in the unstable region, if I start with a homogeneous system and if I make any small perturbation to the system will immediately phase separate. On the other hand, if we are in the metastable region, the system will not phase separate for small disturbances. This is what we refer to as stability. The one way to think about it is you are on the top of a cliff. As soon as you get a small push, you will actually fall down. That will be an unstable case. In the metastable case, you may not be at the minimum, the global minimum of free energy, but you are in some sort of a local minimum. Small disturbances will not lead to a phase separation, even if the final energy is lower than the energy of the state that you are in. You will require larger disturbances for the system to be phase separated into two. Okay, so this will need phase separate with small disturbances, and this will phase separate, will not phase separate for small . So, I can then use these ideas in the next class to talk about what is known as the binodal, spinodal and critical points of a system, and then we will be all set to talk about the polymer solutions. We will start with talking about how do we derive the function f. We will talk about what is known as the lattice model of polymer solutions, and then finally we will apply in the context that we have discussed here and characterize different regions in the phase diagram of polymer solutions based on the function value that we get from the lattice model that we will discuss. So, with that I will stop here. Thank you.